Tonight, we're going to dismantle an image that has been sitting quietly in the back of your mind since you were a child. An image so familiar, so often repeated in textbooks and documentaries and glossy magazine spreads, that you have almost certainly stopped questioning it. Two enormous spiral galaxies, glowing, turning, drifting through the black on an unstoppable collision course. One of them is a stranger, a distant island of 1 trillion stars called Andromeda. And the other one, the smaller of the two, the one you are riding on right now, is ours. You've seen this picture 1,000 times, perhaps in a classroom, perhaps on the cover of a science book, perhaps in a quiet moment scrolling through images of space at night when the world was still and the mind was ready to wander. Two great pinwheels of light tilted toward each other, arms reaching, edges beginning to touch. And underneath the picture always the same confident sentence. In about 4.5 billion years, our galaxy will collide with Andromeda. It is a beautiful sentence. It is a tidy sentence. It is a sentence that feels like a promise. And tonight, we are going to take that sentence apart, slowly, gently, piece by piece, until nothing of it remains. Because here is a question that almost no one asks. A question so strange, so quietly unsettling that it might just keep you up tonight, long after this video has ended and the room around you has gone silent. What does it feel like when the sky itself begins to move toward you? Not a star, not a comet, not an asteroid glinting somewhere out beyond the moon, but an entire galaxy. 600 billion suns, 1 trillion suns coming closer, not for a night, not for a year, but for as long as our species has existed, and for as long as our planet has been able to hold an ocean. That silent, inward drift has been happening the whole time you have been alive. It was happening the day you were born. It was happening the day your grandparents were born. It has been happening for every heartbeat of every creature that has ever lived on this world. And most of us have gone our whole lives without ever quite feeling it. Tonight, we are going to feel it. We are going to walk out to the edge of everything you thought you knew about this collision. And then we are going to keep walking out past the tidy textbook diagram out, past the confident 4.5 billion year timeline, out into a region of new research and revised probabilities where the story you were told begins to fray. We are going to discover together that what actually happens when two galaxies meet is not a collision at all. It is something stranger, softer, almost intimate. We are going to stand under a night sky that no human eye will ever really see, and watch it slowly transform. And then, when we think we finally understand it, we are going to be handed a piece of new science, published only recently, that turns the whole story upside down. A study that quietly, politely, and with the weight of 100,000 supercomputer simulations behind it, says that the collision you were promised may never actually happen. Before we go any further, if you find yourself the kind of person who loves this sort of quiet, deep exploration of the cosmos, a small like or a subscribe would mean a great deal. It is a tiny gesture from you, and it makes an enormous difference for a channel like this one. That's all I'll ask. Now, let's begin. Because the story we are about to tell is not really a story about destruction. It is a story about scale, about how the largest, most violent, most cinematic event you can possibly imagine, at the biggest scale nature offers, turns out on closer inspection to be almost eerily peaceful. It is a story about time, about events so slow that the words fast and slow lose their meaning, and the words beginning and end begin to blur into one long, continuous exhale. And it is a story about certainty, about the way we humans love clean predictions and confident numbers, and how the universe, gently but firmly, keeps reminding us that it does not care what shape our sentences prefer. Over the next hour and a half, we are going to move through this together in slow, deliberate layers. We will start with the picture you already know, the one from the textbook, the one with the two galaxies and the confident arrow and the number 4.5. We will linger there long enough to see how it was built. And then, one crack at a time, we will begin to break it. We will meet a quiet astronomer from the year 1912, the first person on Earth to realize that Andromeda was not drifting away like almost every other galaxy in the sky, but was, impossibly, coming toward us. We will find out what actually happens when two galaxies meet, why stars almost never touch, and why the real drama is not in the light we can see, but in the dark, invisible halos that surround every galaxy like a second, larger body. We will build in our minds the future night sky, a sky where Andromeda swells until it fills the horizon, a sky where our familiar band of the Milky Way is joined by a second, ghostly band, and then a third, and then eventually, in the last act, all of them dissolve into a single dome of scattered stars. And then, when the picture feels almost complete, we will introduce the new science. The study, published just last year, that reduced the odds of that collision from near certainty to something closer to the flip of a coin. And finally, in the last minutes of this video, we will do something a little unusual. We will step back from the question itself. We will ask whether "will they collide" is even the right question to be asking. And we will find, I think, an answer that is more humbling and more strangely comforting than either yes or no. But first, I want you to do something for me. Wherever you are right now, whether you are lying in bed or curled on a couch or driving through a long, quiet night, I want you to picture the image we started with. The two spirals, the confident arrow, the tidy prediction. Hold it in your mind for a moment. Look at how neat it is, how reassuring, how much it feels like something we already understand. And now let me ask you something honest, something personal before we take a single step further. When you first learned that our galaxy was going to collide with another galaxy, how did it make you feel? Did it frighten you? Did it comfort you in some strange way to know that even the sky has a future? Or did it feel abstract, distant, safely tucked away in a number too large to touch you? I want you to remember whatever that feeling was. Because in a moment, we are going to step inside the picture that first gave it to you, and we are going to see it properly, for perhaps the first time in your life. We are going to walk into the textbook. And once we're inside, we are going to notice, very quietly, that some of the lines don't quite match up. So let us step inside the picture. Let us walk together, into the textbook diagram you have carried in your head since childhood, and let us stand there quietly for a while, and let us look at it the way you might look at an old family photograph you have not really examined in years. From a distance, everything seems right. Up close, small strangenesses begin to appear. The picture, as you remember it, goes something like this. Two great spiral galaxies seen from above, or perhaps from a slight angle. One of them is our own, the Milky Way. A flat, luminous pinwheel, some 100,000 light-years across, with a warm yellow bulge at its center and long, curving arms of blue and pink, where new stars are being born. Somewhere along one of those unremarkable arms, on the inner edge of what astronomers call the Orion Spur, a single small yellow star sits with a small blue planet in orbit around it. That is where we live. That is the pale dot from which every human that has ever existed has looked up at the sky. And in the diagram, floating out beyond the Milky Way, tilted at a gentle angle, is the other galaxy. Larger, grander, even more richly patterned, the Andromeda Galaxy. Sometimes called by its catalog name Messier 31 or simply M31. The two galaxies are drawn with an arrow between them. Sometimes the arrow is subtle, sometimes it is bold, and beneath the arrow always there is a number, 4.5 billion years, a collision, a merger. A new galaxy sometimes called Milkomeda. And then the paragraph ends and the page turns, and we are meant to move on to the next chapter of the textbook and file this fact away with all the other facts we have. Remember about the universe. But before we move on, let us really look at Andromeda, because Andromeda is going to be the quiet companion of this entire video, and you should know her properly. Andromeda is not a small thing. She is not a modest neighbor. She is the largest galaxy in what astronomers call the local group, the small cluster of about 100 galaxies to which our Milky Way belongs. She is roughly 220,000 light-years across, which is more than twice the width of our own galaxy. If you could somehow shrink the Milky Way down to the size of a large dinner plate, Andromeda would be the size of 2 dinner plates set side by side. She holds, by most recent estimates, around 1 trillion stars. Say that number slowly. 1 trillion. Our own Milky Way, by comparison, is thought to contain somewhere between 2 and 400 billion, which means, star for star, Andromeda has perhaps 3, 4, 5 times as many suns as we do. And at her very center, she does not merely have a supermassive black hole, as our galaxy does. She has one that is somewhere between 100 and 200 million times the mass of our Sun. The black hole at the heart of our Milky Way, the one we call Sagittarius A star, weighs about 4 million solar masses. Andromeda's central engine is somewhere between 25 and 50 times heavier. It is one of the great, sleeping monsters of our corner of the universe. A dark giant drifting quietly at the center of 1 trillion suns. She is also, and this is the part that always stops me when I think about it, close enough to see. Right now, tonight. If you are somewhere far enough from a city on a clear autumn evening in the northern hemisphere, you can walk outside, tilt your head back, look up toward the constellation Andromeda and find her. She will not look like the picture in the textbook. She will look like a soft gray smudge, a patch of nothing, a little bruise on the black. And that soft, quiet smudge is the light of 1 trillion stars arriving at your eyes after a journey of roughly 2.5 million years. Let that sink in for a moment. The light that lands in your pupil tonight, the light that your retina turns into a signal your brain calls a smudge, that light left Andromeda before there was a single human being anywhere on this planet, before there was writing, before there was fire, before there was language, before, in fact, the species we call Homo sapiens had begun to exist at all. Andromeda is the most distant object that the naked human eye can see. And she has been drifting up there, quietly, in the same patch of sky, for every one of the roughly 100,000 years our species has been looking up. We were not the first to notice her. Around the year 964, a Persian astronomer named Abd al-Rahman al-Sufi, working in the great Islamic astronomical tradition, wrote what may be the earliest surviving description of her. He called her a small cloud. A small cloud, he wrote, in front of the mouth of the fish, using the star patterns of his time. He did not know what she was. He could not have. For 1,000 years after him, people who saw her in the sky assumed she was some kind of nebula, some patch of glowing gas inside our own Milky Way. It was not until the early 20th century that anyone realized what Andromeda actually was. That she was not a cloud inside our galaxy at all, that she was another galaxy, a whole other city of stars, an island universe drifting in a sea of darkness, unimaginably far from our own. And this discovery, when it came, was one of the great humblings of the human mind, because it meant that the Milky Way, which we had thought was more or less everything, was suddenly just one of many, one of hundreds, then thousands, then eventually hundreds of billions. But tonight we are not here for that story. Tonight we are here for a smaller, more intimate story. The story of our galaxy and Andromeda and the tidy little arrow drawn between them. Because the way the textbook tells it, the story is almost cozy. Two galaxies drifting toward each other. 4.5 billion years from now they meet. There is a merger. There is a new galaxy, Milkomeda, a giant elliptical, no longer a flat pinwheel but a fat, hazy ball of stars drifting on into the future. And underneath this description always, there is an unspoken feeling that this is all settled science, that we know, that the numbers are locked in, that the sky, in a very literal sense, has been given its schedule. And this is where the picture, if you look at it long enough, begins to feel a little too neat. Because if you stand there in the textbook diagram for a while, and you look at the two galaxies, and you look at that confident arrow, a few quiet questions begin to rise in the mind. How exactly do we know? How do we measure the motion of a galaxy that is 2.5 million light-years away? How do we track something so distant, so slow, so silent, that its position across the sky barely shifts even over a human lifetime? And what does it actually mean for two galaxies to collide? Do the stars smash into each other? Do the planets burn? Does the sun in our sky wink out one night replaced by fire? The diagram does not answer any of this. The diagram is a shorthand, a summary, a single frame lifted out of a story that runs for tens of billions of years and cropped so tightly that all the strangeness has been trimmed off the edges. And here is the first, gentle little heresy of tonight. The diagram, as you have always seen it, is a lie of omission, not a malicious lie, not a wrong lie, but a comfortable lie, the kind of lie we tell children so that they will not have to hold too much at once. The two galaxies are drawn as if they were solid objects, whole and complete, like two apples about to knock into each other on a table. But galaxies are not apples. They are not even solid. They are almost entirely empty space. The arrow is drawn as a straight line, as if Andromeda were flying at us like a thrown stone, when in fact her motion is a strange, three-dimensional drift whose sideways component is so small that, for almost the entire history of astronomy, we could not measure it at all. And the number, that reassuring 4.5 billion, is the middle of a range so wide that some of its edges disappear into a probability that the collision might not happen at all. None of this is in the picture. And so tonight, we are going to draw a better picture, slowly, layer by layer. We are going to add back in everything the textbook diagram left out. We are going to trace the story from the first faint hint that Andromeda was moving strangely, all the way through to the newest supercomputer simulations, run just months ago, which have quietly rewritten the entire ending. And by the time we are done, I do not think you will ever look up at that soft gray smudge in the constellation Andromeda quite the same way again. But before we take that next step, I want to ask you something. And I want you to sit with it honestly for a moment. When you were younger, when you first learned that Andromeda existed and that she was on her way, did you ever go outside and actually try to find her in the sky? Have you seen her with your own eyes? Or is she still, for you, only a picture in a book, only a name in a documentary, only a soft rumor from someone else's telescope? Because there is a strange, quiet difference between knowing about Andromeda and having stood under her light. I would love to know which one you are. Tell me, in a comment, whether you have ever seen the small cloud that Al-Sufi wrote about 1,000 years ago. Whether you have ever, once in your life, looked up and found the light of 1 trillion stars and let it fall into your eyes. Because in a moment, we are going to leave the tidy diagram behind. We are going to walk out of the textbook and into a small observatory, high in the mountains of Arizona, in the year 1912. There, a quiet young astronomer named Vesto Slipher is going to point a telescope at that same soft gray smudge, and he is going to notice something so strange, so out of place, that it will crack the entire cozy picture wide open. Because almost every galaxy in the universe, as we will see, is moving away from us, fleeing outward, retreating into the dark. But this one, this single particular smudge, is doing the opposite. This one is coming closer. And no one in all of human history has ever quite known what to do with that fact. Picture, then, a small observatory in the mountains of Arizona in the year 1912. It is called the Lowell Observatory, perched on a ridge above the little town of Flagstaff, at an elevation of about 7,000 feet, where the air is thin and the winter nights are cold and unspeakably dark. There is no light pollution here, not yet. There are no highways beneath the ridge. There are no glowing screens in warm windows. The town below is a small pool of gas lamps, and above it, in every direction, the sky is thick with stars. The Milky Way pours across the darkness from horizon to horizon, so bright that on a moonless night it casts a faint shadow on the ground. And inside the observatory, in a chilled dome that is open to the sky, a young man in a heavy coat is bent over the eyepiece of a 24-inch refracting telescope. His name is Vesto Slipher. He is 37 years old. He is patient, meticulous, and almost pathologically shy. And on this particular night, he is doing something that no one has ever quite done before. He is trying to measure the speed of a smudge. The smudge, of course, is Andromeda. Except in 1912, no one yet calls her Andromeda the Galaxy. No one is even sure what she is. The prevailing view among most astronomers of the time is that she, and all the other soft, spiral-shaped smudges scattered across the sky, are simply nearby clouds of glowing gas, tucked somewhere inside our own Milky Way, little pinwheels of hot vapor. Local weather on a cosmic scale. The very idea that they might be entire other galaxies, complete and separate, floating out in a vaster darkness, is still considered by most respectable scientists to be a fringe speculation. It will take another decade, and the patient work of a young Edwin Hubble at Mount Wilson, before that debate is truly settled. But Slipher, on this cold Arizona night, is quietly gathering the evidence that will change everything. He is not looking directly at Andromeda's light. He is not trying to see her more clearly. He is doing something subtler. He is spreading her light out. He has attached a device called a spectrograph to the eyepiece of the telescope, a beautifully simple instrument that takes incoming light and splits it, the way a raindrop splits sunlight into a rainbow, into all its component colors. Every element in nature, when it glows, leaves a specific fingerprint on that rainbow. Hydrogen has its own set of dark and bright lines. Calcium has another, iron another. And these fingerprints, these little vertical bars along the spectrum, are as fixed and reliable as anything in physics. They are the barcode of the universe. But here is the trick. If the object emitting the light is moving toward you, all of those little vertical bars shift slightly toward the blue end of the spectrum. If it is moving away from you, they shift toward the red end. It is the exact same phenomenon you have heard your whole life, only in light instead of sound. Think of an ambulance passing you on a road. As it approaches, its siren sounds higher. As it recedes, its siren sounds lower. The sound waves are being compressed in front of it and stretched behind it. Light does the same thing. Compressed light bunches toward the blue. Stretched light drifts toward the red. Astronomers call these two effects blueshift and redshift. And by measuring very precisely how far the fingerprint has shifted along the spectrum, you can calculate with astonishing accuracy how fast the object is moving toward you or away from you. Not roughly, not approximately, to within a few kilometers per second. This is what Slipher is doing on that cold night in Flagstaff. He is not looking at Andromeda. He is listening to her siren. And he is doing it with an extraordinary amount of patience because Andromeda is faint. Even through a 24-inch telescope, her light, spread out into a spectrum, is barely enough to expose a photographic plate. He has to hold the telescope on her, tracking her motion across the sky with tiny hand-cranked adjustments for hours. Sometimes for multiple nights in a row, the same plate reopened, the same faint light patiently accumulating, until at last there is enough exposure to develop. And when he finally develops that plate and he holds it up to the light and he measures the position of those little vertical bars, he finds something that stops him cold. The bars have shifted, not toward the red, toward the blue, and not by a small amount. By an enormous amount. He runs the calculation. He runs it again. He does not quite believe it. The number he keeps arriving at is around 300 kilometers per second. 300 kilometers per second. That is the speed at which Andromeda, whatever she is moving toward the Earth. That is more than 1,000,000 kilometers per hour, faster than any object he has ever measured, faster than the fastest star known. And it is not moving away, as almost every other faint smudge in the sky, once he begins to measure them, turns out to be doing. It is coming toward us. He writes it up quietly in a short scientific paper. He does not shout about it. He does not tour the country giving lectures. That is not his temperament. He simply publishes the number and lets it sit there in the record. And the number at the time is so strange, so much larger than anyone expected, that most astronomers do not quite know what to do with it. It will be years before anyone begins to understand what it truly means. But in retrospect, that quiet measurement in Flagstaff in 1912 is one of the most important observations in the entire history of astronomy. It is the first time a human being ever measured the motion of a galaxy. And the very first galaxy anyone ever measured was heading directly toward us. Now, sit with that for a moment, because this is the first crack in the tidy textbook picture. This is where the story begins to feel real and not diagrammatic. Andromeda is not just floating out there, waiting for some far future rendezvous. Andromeda has been coming toward us the entire time. She was coming toward us when Slipher first measured her light. She was coming toward us when the pyramids were built. She was coming toward us when the first fish crawled out of the sea. She was coming toward us before there was a sun in this sky, before there was an earth beneath your feet, before the elements that make up your bones had been forged inside dying stars. That silent, inward drift is not a future event. It is a present tense condition of the universe. It is happening right now. And in the time it has taken you to listen to this sentence, the two galaxies have moved perhaps 200 kilometers closer together. 200 kilometers over a distance of 2.5 million light years. It is, at that scale, nothing. It is a whisper. It is a fingertip's worth of motion across a continent. And that is the strangest thing of all about this collision. Its speed by any human standard is enormous, roughly 110 kilometers every second along our line of sight. If you add in the sideways drift and account for the motion of our sun around the Milky Way, the two galaxies are closing on each other at somewhere close to 400,000 kilometers per hour. That is more than 100 kilometers per second. It is faster than a bullet, faster than any spacecraft we have ever launched. And yet, spread across the ocean of space between us, this dizzying speed becomes almost invisible. It will take billions of years for that motion to add up to anything you or I would recognize as an approach. The galaxy is barreling toward us, and also, from our point of view, it is standing perfectly still. This is the first strangeness. The first place where our human intuitions begin to fail. We are used to collisions happening on human timescales. Two cars on a highway, two waves at a beach, a ball meeting a bat. Every collision we have ever experienced or watched has happened in seconds or fractions of seconds. But this collision, this cosmic collision that we speak of so casually, is not one event. It is a process. It is a slow, silent, 4 billion year long process that has already been going on for at least 10 billion years. Ever since our two galaxies first began to feel each other's gravity across the void. Slipher did not discover the beginning of the approach. He simply discovered that we were already inside it, that we always had been. And there is a second strangeness hidden in his measurement, one that took decades for astronomers to fully appreciate. Because when Hubble at Mount Wilson, a few years later, began to measure the light of other distant galaxies, he discovered something that would change our understanding of the entire cosmos. Almost every galaxy he looked at was redshifted. Its fingerprints were sliding toward the red, which meant that almost every galaxy in the universe was moving away from us, retreating outward, and the farther away a galaxy was, the faster it was fleeing. This was the discovery of the expansion of the universe. The realization that the fabric of space itself is stretching, carrying every galaxy away from every other galaxy at speeds that grow with distance. It was and remains one of the great revelations of physics. And it means that the ordinary condition of a galaxy out there in the deep universe is to be running away from us, to be a small red-shifted light receding into the dark. Andromeda is one of the very few exceptions. One of a small handful of galaxies close enough to us that gravity, on the local scale, has overwhelmed the gentle push of cosmic expansion. Inside our own local group of about 100 galaxies, cosmic expansion has not won. Gravity has. The galaxies here in our small cosmic neighborhood are still bound to each other. They still orbit each other. They still, sometimes, fall toward each other. And Andromeda, our large, bright, trillion-star neighbor, is falling toward us. Not because the whole universe is doing it. Almost no other galaxy is. She is falling toward us because we are close enough that our own gravity, and the gravity of everything else in our little island group, has been quietly pulling her in for as long as the universe has existed. She is not being carried by the flow of the cosmos. She is swimming against it. There is something almost tender about that when you sit with it long enough. Out of hundreds of billions of galaxies in the observable universe, out of a night sky in which almost everything is fleeing, This one bright neighbor is coming home. And so the tidy diagram, the one in the textbook, is not exactly wrong, but it is missing so much. It is missing the century of patient work that went into measuring that inward drift. It is missing the strange fact that we could measure Andromeda's motion toward us long before we could measure her motion sideways across the sky. It is missing the century-long argument about what Andromeda even was, and the extraordinary moment in the 1920s when the astronomer Edwin Hubble, working with a slightly larger telescope on a mountain in California, finally proved that she was not a cloud of gas in our own galaxy, but another galaxy entirely, and in doing so expanded the known universe by a factor of 1,000. It is missing, above all, the strangeness of scale, the strangeness of that slow, silent approach, a motion so fast that it defies belief and so slow that it defies the imagination, both at the same time. Which brings us to a question I would love for you to answer honestly. Have you ever, in your own life, had one of those moments where you learned that something you had always assumed was actually in motion? A friendship, perhaps, or a job, or a place you thought would always be the same. And then one day you realized it had been drifting the whole time, and you had simply been too close to notice. Because that, in a way, is what Slipher's measurement in Flagstaff was, on a cosmic scale. It was the moment humanity realized that the sky was not still, that even the fixed and eternal-seeming stars were in motion, that whole galaxies were traveling and falling and coming toward us in the dark. Have you ever had a version of that moment in your own small life? Tell me in the comments. I would love to hear. Because in a moment, we are going to take Slipher's number, that quiet blueshift on a photographic plate, and we are going to ask the next question. The obvious question. The question that seems at first to have an obvious answer. If Andromeda is coming toward us and we are coming toward her, and we can measure how fast, then surely we can imagine what will happen when they meet. Surely we can picture the collision. Two galaxies closing at 400,000 kilometers per hour over a distance of 2.5 million light years. Surely when they finally arrive, there will be fire. There will be light. There will be stars smashing into stars, and planets exploding in bright pulses across the sky, and worlds burning in the crossfire of a slow-motion catastrophe. That is what the word collision means, isn't it? That is what it has always meant. Except, as we are about to see, when it comes to galaxies, that word may be the most misleading word in the entire language of astronomy. Because what actually happens when two galaxies meet is not a collision at all. It is something much stranger, much quieter, and in a way that will take the next section of this video to unfold, almost impossibly gentle. So let us picture for a moment what most of us imagine when we hear the phrase galactic collision. Two great spirals drifting toward each other in the dark. As they close, the outer stars begin to touch, then more, then more. Fireworks bloom along the seam where they meet. Stars smash into other stars in blinding flashes. Planets are pulverized. Whole solar systems are torn apart in a slow-motion firestorm. The two galaxies grind together in a screaming crush of light and heat, until at last, exhausted, they settle into one great glowing wreckage in the middle of the sky. Almost everything about that picture is wrong. I want you to hold that in your mind for a moment because it is one of the strangest and most beautiful revelations that astronomy has to offer. When two galaxies meet, almost nothing collides. Not the stars, not the planets, not in almost any meaningful sense the matter that we can see. The event we so casually call a collision is, at the level of individual objects, an almost perfect near miss. Trillions of near misses, one after another, over the course of billions of years. The word we should really be using is not collision. It is dance. Or perhaps, if we are honest about how quiet and how eerie it will be, a ghost dance. Two great transparent shapes drifting through each other in the dark, each one made almost entirely of empty space, each one gliding through the other as if the other were not really there at all. To understand why, we have to talk for just a moment about how staggeringly empty a galaxy actually is. And this is where our human intuitions fail us most badly. Because when you look up at the summer sky and see the band of the Milky Way, thick and creamy across the darkness, it does not look empty. It looks crowded. It looks packed. It looks like a great river of light. But that appearance is a trick of perspective. What you are seeing is the accumulated light of hundreds of billions of stars, stretched across a disk 100,000 light years wide, all crushed by the geometry of your eye into a thin, bright band. Up close, if you could stand between two stars and look around, the picture would be entirely different. It would be almost entirely empty black. Here is the way astronomers like to describe it. Imagine for a moment that you shrink our sun down to the size of a ping-pong ball, a small white sphere sitting in the palm of your hand. At that scale, how far away would the nearest other star be? The nearest star to our sun is a small red dwarf called Proxima Centauri. Real distance, about 4.2 light years. At our ping-pong ball scale, Proxima Centauri would be another small ball, not next door, not down the street, not across town, but roughly 1,100 kilometers away. That is the distance from New York to Chicago and back again, from London to somewhere well into Eastern Europe. That is the average spacing between neighboring stars in our part of the galaxy. Two ping-pong balls separated by a continent. And in between them, in that vast dark distance, essentially nothing. A few scattered atoms of hydrogen per cubic meter, a thin whisper of interstellar dust, and silence. Now imagine two such continents drifting through each other. Every ping-pong ball on one continent is passing through the airspace of every ping-pong ball on the other. What are the odds that any two of them actually touch? Almost zero. Not because it is impossible, but because the ratio of solid matter to empty space, at the scale of a galaxy, is so absurdly small that the numbers begin to feel almost comedic. Astronomers who have run these calculations estimate that, in the entire course of the merger between our Milky Way and Andromeda, over the 4 or 5 or 6 billion years it will take to unfold, the number of actual star-on-star collisions may be 0, or 1, or maybe a small handful, Out of the more than 1 trillion stars involved, let that number sit with you for a moment. Trillions of stars moving through each other, and almost none of them ever coming close enough to feel each other's heat. Which means, and I want you to hear this clearly if you are standing on the surface of the Earth on the day that Andromeda passes through the Milky Way, and if by some miracle the Earth is still here, and the Sun is still here, and human eyes still exist to look up, you will not see fireworks. You will not see stars crashing together in bright flashes. You will not see fire in the sky. The sky will simply get more crowded. Slowly, silently, over millions of years, the familiar constellations will be joined by others. New bright stars will appear where before there was only faint background. The dust lanes of Andromeda will begin to overlap with our own, and the great sweeping arms of her spiral will bend and pull and stretch into shapes no astronomer has ever mapped. It will be one of the most beautiful and one of the most utterly quiet transformations in the history of this piece of the universe. A cosmic apocalypse that a human observer standing on a hillside would experience as a silent, almost imperceptibly slow rearrangement of the stars. And yet, and this is the twist, the fact that individual stars almost never touch does not mean the collision is not real. It is real. It is enormous. It reshapes both galaxies utterly. But the drama is happening at a different level than most of us imagine. It is happening in the invisible. Because the stars you can see, the trillions of glowing pinpricks, are only the tip of the iceberg. Every galaxy, our own included, is wrapped in a vast, invisible halo of dark matter. This is one of the strangest and most humbling discoveries of 20th century astronomy. Roughly 85% of the matter in the universe does not glow, does not shine, does not emit light of any kind, and does not seem to interact with light in any way we can detect. We cannot see it. We cannot touch it. We do not yet know what it is made of, and yet it is there everywhere because we can measure its gravity. Galaxies rotate too fast to be held together by their visible mass alone. Something is holding them together, something huge, something invisible, something that outweighs all the shining stars by a factor of 5 or 6 to 1. We call it dark matter, which is essentially just a placeholder name, for we do not yet know what this is. And here is the crucial point for our story. The visible disk of the Milky Way, the beautiful pinwheel you know from the textbook, the pinwheel with its arms and its bulge and its warm central glow, is embedded inside a much larger, roughly spherical cloud of dark matter that extends far beyond the edge of the visible disk. The same is true of Andromeda. Each of these galaxies, if you could somehow see their dark matter, would look less like a flat disk and more like an enormous ghostly egg, several times wider than the visible galaxy itself. And these ghostly eggs, these invisible halos, are actually already touching, or nearly so. The outer edges of the Milky Way's dark matter halo and the outer edges of Andromeda's dark matter halo have almost certainly begun to overlap, quietly, unnoticeably, right now. The collision has already started, at a scale that no human instrument has yet been able to see. What we call the collision, the moment when the visible galaxies begin to merge, is really just the last, most dramatic act of a much slower, much larger process that has been unfolding for a very long time. And it is these dark matter halos more than anything else that drive the story of the merger. Because as the two halos overlap and pass through each other, they do interact, not through collisions in the ordinary sense, but through gravity. Each halo tugs on the other. Each halo feels the presence of the other and pulls back. The result is a kind of gravitational drag, a friction, but a frictionless friction, mediated entirely by gravity. As the two galaxies drift through each other, energy is quietly drained out of their motion and spread into the vast, invisible halos around them. The galaxies slow down. Their orbits tighten. They lose the ability to simply pass through each other and drift apart again. And so, over the course of billions of years, they are gently, inexorably pulled together and locked into a slow, inward spiral. This is called dynamical friction. It is one of the loveliest ideas in astrophysics. And it is the single most important force in the story of what is coming. Now, layered on top of this invisible tug-of-war, there is another kind of drama. And this drama, unlike the ghostly gravitational one, will actually be visible. It has to do with gas. Because unlike stars, which are so far apart that they almost never collide, the diffuse clouds of hydrogen gas that drift between the stars are much larger. They fill vast volumes. They are the raw material from which new stars are born. And when two galaxies pass through each other, their gas clouds absolutely do collide. They slam together, they compress, they heat up. And in the shock waves of that compression, something extraordinary happens. Star formation begins, explosively. In some regions of the merged galaxies, new stars will be born at rates dozens or even hundreds of times higher than the calm, sleepy rate at which the Milky Way currently makes stars. Astronomers call these events starbursts. And we can already see them, right now, in other pairs of galaxies caught in the act of merging. If you have ever seen images of the so-called antennae galaxies, or the mice, or NGC 4676, you have seen what this looks like. Two spirals mid-embrace, their arms drawn out into long luminous streamers by tidal forces, their cores tangled together in a bright knot, and along the seams where their gas is being crushed, whole galleries of new blue star clusters lighting up like sparks along a fuse. That is our future. Not in every detail, but in the essential shape. That is what the Milky Way and Andromeda will look like to some distant observer, some faraway galaxy in another cluster, 1 or 2 billion years from now. Two beautiful pinwheels, distorted, stretched, their arms flung out into long tidal streamers, their gas alight with new stars, drifting slowly together in the dark. And here is another quiet strangeness. During the merger, some stars will not stay with their home galaxy. As the two galaxies pass and repass through each other, gravity will fling some stars out into intergalactic space entirely. They will be launched at hundreds of kilometers per second out of the visible bounds of any galaxy at all. Astronomers call these hypervelocity stars, or more evocatively, exiled stars. They will drift for the rest of eternity between the galaxies, alone in the dark, illuminated by nothing but their own light. Whether our sun will be among them, whether some future version of the Earth will find itself flung out into intergalactic space, is one of the small, quiet uncertainties buried inside every simulation of the merger. In some simulations, the sun stays close to the crowded core of the newly forming galaxy. In others, the sun is thrown far out into the halo, into a place where the night sky would look very different, a place with fewer stars overhead, a place with more darkness, a place from which the merged Milky Way and Andromeda in the distance would look like a single glowing island and everything else would be black. That is one possible destiny for our little corner of the universe. Not death, not fire, exile. There is one more actor in this drama, and I want to name her, because she is the most quietly terrifying of them all. At the very center of the Milky Way, there is a supermassive black hole. We call her Sagittarius A star. She is about 4 million times the mass of our sun, and she sits at the gravitational heart of our galaxy, wrapped in a thin ring of orbiting stars and gas. And at the very center of Andromeda, there is a much larger supermassive black hole. Somewhere between 100 and 200 million times the mass of our sun, 25 to 50 times heavier than ours. And as the two galaxies merge over the course of billions of years, these two black holes will be drawn, slowly and inexorably, toward each other. They will spiral inward. They will orbit each other in ever-tightening loops. And eventually, in the last act of the merger, they will collide. And when they do, they will release a burst of gravitational waves so powerful that they will ring the fabric of spacetime itself, sending ripples out across the entire universe. That collision, unlike the collision of the galaxies as a whole, will not be quiet. It will be one of the loudest events in the entire history of this region of the cosmos. And it will happen at the very center of the merged galaxy, in a place where, by then, the human eye, if any still existed, would already be seeing something entirely unfamiliar. Which is where our story is heading next, because so far we have been talking about the mechanics of the collision. What actually happens? What actually touches? What actually merges? But we have not yet talked about what any of this will look like from the ground. From a hillside on the earth, from a pair of eyes upturned to the sky. And that, I think, is the part of this story that will stay with you the longest, because the collision is not really an event in the sky. The collision is the sky. It is a slow, silent, breathtaking transformation of the night itself, unfolding over billions of years, in which the familiar band of the Milky Way we have known our whole lives is gradually joined, and then overtaken, and then finally replaced by something no human eye has ever seen. But before we go there, I want to ask you a question, and I want you to sit with it a little. When you first learned, tonight or maybe years ago, that stars almost never actually collide when galaxies merge, how did it change your picture of what a galactic collision is? Does it feel less dramatic to you, knowing that the fire and the fury you had imagined were never really there? Or does it feel more haunting, more strange, more beautiful in a quieter way? because there is something in me that finds the truth of it, the silent ghost dance of trillions of stars drifting past each other in the dark, far more moving than any storm of fire could ever have been. I would love to know how it lands with you. Tell me in the comments, because in a moment, we are going to leave the mechanics behind. We are going to stop asking what will happen and start asking what it will look like. We are going to walk out onto a hillside, 500 million years from now, and 1 billion, and 2, and 3, and we are going to stand there in the future and watch the sky slowly change. We are going to watch Andromeda grow. We are going to watch the two galaxies begin to pull each other apart into long, luminous streamers. And we are going to watch, at last, the birth of a new galaxy and the death, in the very same moment, of the sun that made us. So let us go there. Let us step off this hillside, this present moment, this small, quiet room in which you are listening, and let us walk out into the deep future, not by leaping to the end, but slowly, in stages. The way you might walk out into a field at dusk and stop and look up and let your eyes adjust, and then walk a little farther and stop again and look up once more, and find that the sky above you has changed while you were not quite watching. Because this is how the merger will actually unfold, not as a single event, not as one great cataclysmic night, but as a slow, cinematic, 4 to 6 billion year transformation of the sky itself, in which every generation of eyes, if any could exist to see it, would look up and find that the sky was very slightly different from the one their grandparents had known. Nothing sudden, nothing violent, just an almost imperceptible drift night after night, century after century, epoch after epoch, until the sky was no longer the sky at all. Let us start close. 500 million years from now, the Earth, if it is still here, is a strange place. The sun is a little brighter than it is today. Slowly, patiently, over billions of years, our star has been growing hotter as it burns through its hydrogen. In 500 million years, it will be bright enough that the oceans on the surface of the Earth will be in trouble. Perhaps the Earth by then will be a different world entirely, with different continents, different life, or perhaps no life at all. But let us set that aside. Let us imagine, for the sake of the story, that some pair of eyes is still there, upturned to the sky. What would they see on a clear moonless night when they look toward the constellation we currently call Andromeda? They would see her still as a soft glow in the darkness, but she would no longer be a small smudge. She would be visibly larger than the moon, not brighter but wider. A soft, luminous oval stretched across a patch of sky several times the size of the full moon. On a clear country night, 500 million years from now, Andromeda would be one of the most striking features in the sky. A pale, ghostly presence. A soft cloud with structure inside it, hints of spiral arms, hints of a bright core. She would still be far away, millions of light years still. But she would be close enough now that even without a telescope, without any instrument at all, her true nature would be obvious. She would look from Earth like what she actually is. Another galaxy, a whole other city of stars hanging in the sky. Now let us walk a little further into the future. Let us stand in that same field on that same continent, 2 billion years from now. 2 billion years is an enormous number. It is roughly the amount of time between now and the age when the Earth first had complex, multi-celled life in its oceans. It is nearly half the age of our planet. And in that vast span of time, Andromeda will have crossed a great deal of ground. She will now be so large in the sky that she is impossible to ignore. She will fill a fifth of the visible heavens, maybe more, a great luminous smear pouring across the night. Her spiral arms will be plainly visible to the naked eye. Her bulge will glow like a second, softer moon. And quietly, unnervingly, the Milky Way itself will have begun to change. Because at this stage, the two galaxies are close enough that they have begun to feel each other properly. The outer arms of our own galaxy are starting to bend under the pull of Andromeda's gravity. The dust lanes are beginning to warp. The gentle, well-organized spiral we know from every diagram is beginning, ever so slowly, to lose its shape. At 3.5 billion years from now, we reach the first close encounter. This is one of the great moments of the merger. The two galaxies do not collide, not properly, not yet. They pass each other. Astronomers call this a close paracentric passage, a fancy phrase for a very intimate flyby. The Milky Way and Andromeda will glide past each other at a distance of only tens of thousands of light years. Close enough that their outer regions are entangled, close enough that their gas clouds slam into each other and light up in vast starburst episodes, close enough that the sky from the surface of the Earth will be almost unrecognizable. Let us stand there for a moment, under that sky. Andromeda now fills the horizon. Half of the visible sky is her, drawn out into long tidal streamers, her arms flung like ribbons across the darkness. In some directions, you can see her core glowing warmly through the arch of her spiral. In other directions, her stars are so densely packed that they form a second Milky Way, a second bright band cutting across the sky at an angle to our own. Between the two bands, along the seam where their gas has collided, whole regions of the sky are lit up with the pink glow of stellar nurseries. Newborn stars, some so massive and bright that they will burn out in only a few million years, dot the sky in clusters, in strings, in luminous knots. There are more bright stars in the sky than any ancestor of yours ever saw. Constellations, as human beings have known them for 100,000 years, are gone, not dimmed, not shifted, gone, replaced by an entirely different sky, a sky no human civilization has ever known, a sky that no human eye in all likelihood will ever see. And then, slowly, as the two galaxies pass each other, this incredible sky begins to change again. Because a close paracentric passage is not the end of the story. It is only the first act. The two galaxies, having passed through each other once, do not simply drift apart. They cannot. The invisible gravitational drag of their dark matter halos has already begun to slow them down. Energy has been quietly bled out of their motion into that vast, unseen envelope, and so they cannot escape each other. They will loop out to some maximum separation, perhaps hundreds of thousands of light years apart, and then, like two dancers who cannot let go, they will fall back toward each other again, and again, and again. Somewhere between 4 and 5 billion years from now, the two galaxies will merge in earnest. Not in one single moment, but in a long, slow, inward spiral. The two spiral disks, already deformed from the first passage, will smash and warp and reorganize themselves. The two supermassive black holes at the two galactic centers, our own Sagittarius A star, only 4 million times the mass of the Sun, and Andromeda's much larger central engine, 1 to 200 million solar masses, will fall toward each other. They will find each other. They will begin to orbit at first slowly, and then faster and faster and faster, sinking inward through a haze of stars and gas. And eventually, in a final crescendo, they will collide. When they do, a burst of gravitational waves will ring out across the fabric of space-time, so powerful that if any advanced civilization anywhere in the observable universe still exists to listen, they will feel that ringing pass through their world like a bell struck at the center of everything. A merger of two supermassive black holes is one of the loudest events physics allows, and it will happen at the very center of the sky we have been watching change. By the end of all of this, somewhere between 5 and 6 billion years from now, the merger will be essentially complete. The two spirals, the two great pinwheels, will be gone. Their disks will have been broken and reorganized into a single, roughly ball-shaped galaxy. Astronomers call this kind of shape an elliptical galaxy. It is the fate, we believe, of most large spiral galaxies that fall into each other. The neat, flat, ordered rotation of a spiral is a delicate thing. Once it has been disturbed by a merger of this scale, it is very difficult to put back together. And so the great pinwheel of the Milky Way, the great pinwheel of Andromeda, will both be gone. In their place, a single new galaxy, a quieter one, a dimmer one. Its gas mostly used up in the great starburst episodes of the merger. Its bright, blue, massive stars mostly dead. Its remaining stars mostly old, mostly red, mostly slow. It will still contain more than 1 trillion stars. It will still glow warmly against the dark. But it will not have arms. It will not have a bulge. It will look from a great distance like a soft, glowing ball of light drifting through the intergalactic dark. This new galaxy has a name, or rather 2 names. Some astronomers call it Milkomeda, others call it Milkomeda. Both are portmanteaus of the 2 parent galaxies. Both are attempts by scientists, in a rare moment of whimsy, to give the new galaxy an affectionate handle before it exists. And both, if I am honest, feel a little too playful for what they describe. Because Milkomeda is not simply a bigger galaxy. Milkomeda is the final act of a great cosmic performance. Milkomeda is what remains after the great collision that took our sky apart and put it back together again as something new. And here is the twist that I want you to sit with for a moment. Because there is one detail in this timeline that I have not yet mentioned, and it is the detail that, for me, gives the whole story its emotional weight. Milkomeda will finish forming by most simulations roughly 5 to 6 billion years from now. And in almost exactly that same window, 5 to 6 billion years from now, our sun will die. Not die in an instant, not vanish, but begin the long, dramatic ending of its life. Our sun right now is a middle-aged star. It is about 4.5 billion years old, and it has enough hydrogen in its core to shine, more or less as it does today, for perhaps another 5 billion. And then, its fuel dwindling, it will begin to swell. It will expand outward. It will grow into a red giant, its outer layers swelling until it swallows Mercury, and then Venus, and probably, at some point in that long agony, the Earth itself. And then, over the course of 100 million years or so, the sun will slew off its outer layers into a beautiful expanding shell called a planetary nebula, and the core that remains will settle down into a slowly cooling ember called a white dwarf. That is the end of our star. That is the end of our small yellow companion in the sky. And this ending, this quiet stellar death, will be happening in the same window as the birth of Milkomeda. I want you to feel the poetry of that for a moment, because it means that in some very real sense, the sun and the merged galaxy are on the same schedule. The sun will be ending its life as the two galaxies are finishing their embrace. There will be, perhaps, a few billion years of overlap. A few billion years in which the sun is bloated and red, and the sky above the earth, if the earth is still there, and if human eyes still exist to look up, will be lit not by the familiar pinwheel of the Milky Way, but by the strange, growing, chaotic sky of the merger. And then, when the sun finally dies and its outer layers drift out into space, and the Earth is either engulfed or, at best, an airless, blackened rock in a lengthened orbit around a slowly cooling ember, there will still be Milkomeda in the sky. A new galaxy, a quiet elliptical, its wildness spent, its starbursts long over, its trillions of stars slowly aging in their new arrangement, drifting on through the dark. There is a symmetry to it that almost feels intentional. Almost, but not quite, because it is a coincidence. The sun's lifespan and the merger's timeline are not causally linked. It just happens, by the accident of when we exist inside cosmic history, that the death of our star and the birth of Milkomeda are almost the same event. If you had asked me, before I first learned this timing, what the strangest fact about the Milky Way, Andromeda merger was, I might have said something about the size of Andromeda's black hole, or the emptiness of the galaxies, or the way stars almost never touch. But now, having sat with it for a long time, I think the strangest fact is that the sun will be dying as Milkomeda is being born. And so the sky that we have been building, this magnificent transformed sky, is not really our sky. It is not the sky of anyone we can meaningfully call us. There will be no humans in any recognizable form to see the first close passage. There will be no humans to see the second. There will certainly be no humans to see the moment the two black holes finally collide at the center of the sky. Perhaps other things, perhaps other minds, perhaps whatever life the Earth manages to grow in the strange late centuries before the sun's expansion, or whatever descendants of ours, if any, have found their way to other worlds, but not humans as we understand ourselves. This is a future sky in a very deep sense. It is a sky that belongs to strangers, It is a sky we can only ever see in our own minds, standing here, 5 billion years too early, imagining it into being. And I want to leave you with a question before we move on, because I have been thinking about it while I was writing this, and I would love to know how you feel about it. If you knew with absolute certainty that the merger was going to happen, and that Milkomeda was coming, and that the sky in 5 billion years would be more beautiful than any sky humanity has ever known, but no descendant of yours, no human being, no eye you could ever meet would ever see it, would you still find it beautiful? Would it still matter to you? Is there something wonderful about a beauty that no one you will ever meet will get to witness? Or does it need an observer to be worth anything at all? There is no right answer. I ask because I do not know how I feel about it myself. Tell me in the comments what you think. Because in a moment, everything we have just built, this cinematic, cathedral-scale vision of Milkomeda and its slow birth over billions of years, is going to be gently and quietly challenged. Because just last year, a small team of astronomers in Finland and England ran a set of simulations, 100,000 of them, using data so new that most of the textbooks in the world have not yet caught up. And when they were done, they had a new number. And the number they found was not 4.5 billion. It was not a certainty. It was something closer to the flip of a coin. It might not happen at all. So let us set the beautiful cinematic sky aside for a moment. Let us keep Milkomeda in the back of our minds, still glowing softly at the far end of the timeline, and let us walk back down out of the future and into a small, quiet room in the year 2025. Not an observatory, not a mountaintop, just a room with computers and a group of astronomers standing around a screen looking at the results of a calculation that has been running for many months on some of the fastest machines in Europe. What they are looking at is a set of probabilities. And what those probabilities are telling them is that the story you have just heard, the story of the 4.5 billion year timeline, the story of the inevitable merger, the story of Milkomeda, is not, in fact, as certain as anyone thought. This is where the science, quietly and politely, rewrites the ending. The team is led by an astronomer named Sawala at the University of Helsinki, working with collaborators from Durham University in England, from Toulouse in France, from Edinburgh, from Australia. And what they have done is something no one had quite done at this level of detail before. They have taken the very best current measurements of every relevant object in this cosmic story, not just the Milky Way and Andromeda, but every important galaxy in our local group, and they have fed all of it into a supercomputer. And then, they have not run one simulation. They have run 100,000, each with slightly different starting conditions, each accounting for a slightly different possibility about how much mass Andromeda actually has, or how fast she is really moving sideways, or how heavy her dark matter halo really is. 22 different variables in total. 22 knobs, each of which we cannot yet measure with perfect precision, each of which changes the story slightly if you turn it. And by running 100,000 universes forward through time, they were asking a very simple question. In how many of these universes do the two galaxies actually collide? The answer, published in the journal Nature Astronomy in June of 2025, was startling. In the next 4 to 5 billion years, the window in which the classic prediction confidently placed the merger, the probability of an actual collision turned out to be less than 2%. Less than 2%. Read that number back to yourself. For over a century since the very first hints from Slipher's spectrograph, we have been telling ourselves that the collision was coming and coming soon on the scale of cosmic time. 4.5 billion years. Tidy, confident, definite. And now, 100,000 simulations later, that number has collapsed to a coin toss so lopsided that it is barely a coin toss at all. 98% of the possible universes, given what we currently know, do not have a Milky Way, Andromeda collision inside the classic window. If you extend the clock all the way out to 10 billion years, the picture changes. Over 10 billion years, the probability of a collision rises to roughly 50%. A true coin flip. Not certainty, not even likelihood really, just a shrug of the universe. So how did the story change so dramatically? What did the old picture miss? The answer, it turns out, is that the old picture was too simple. For most of the last century, our understanding of the coming collision was based on treating the two galaxies almost as if they were alone in space. Just the Milky Way, just Andromeda, two objects, one trajectory, one prediction. It is a beautifully clean problem mathematically. Two bodies pulling on each other under gravity. Physics students have been solving problems like this since Newton, but the actual universe is not a two-body problem. It is a many-body problem. And the Milky Way and Andromeda do not float in isolation. They are the two largest members of a small crowd, the local group, roughly 100 galaxies, most of them small dwarfs, but a few of them substantial enough that their gravity matters. Two of those neighbors in particular turn out to matter enormously. The first is a small, ragged galaxy hanging just outside the disk of the Milky Way, easily visible from the southern hemisphere as a faint smear in the night sky. She is called the Large Magellanic Cloud. She is about 10% as massive as the Milky Way, which sounds small, but is actually enormous compared to any other satellite our galaxy has. And she is not just orbiting quietly. She is in the middle of a long, slow, gravitationally violent interaction with the Milky Way itself. And here is the key point. As she swings around us, she tugs at us. She pulls the Milky Way slightly sideways, not much on any given day, but over billions of years, that sideways tug adds up. It nudges the entire Milky Way ever so slightly off the collision course that the old models had confidently drawn. The second neighbor is called Triangulum, or, in the catalog, Messier 33. She is the third largest galaxy in our local group. She sits more or less near Andromeda, and she is gravitationally bound to her. And she does to Andromeda what the Large Magellanic Cloud does to us. She tugs, she nudges, she perturbs. Any prediction that ignores M33 is ignoring an actor who is standing right on the stage. For most of the 20th century, We simply did not have precise enough measurements of any of this to do the calculation properly. The transverse motion of Andromeda, her sideways drift across the sky as opposed to her motion straight toward us, was for decades one of the great missing numbers in astronomy. Slipher could measure her motion toward us in 1912 because that motion showed up as a spectral shift. But her sideways motion, her drift across the field of view, is so small at that distance that it took the exquisite precision of the Hubble Space Telescope, and then the even finer precision of the European Space Agency's Gaia mission, to begin to nail it down. And even now, the numbers come with real uncertainties. The Sawala team in their study took all of these uncertainties seriously, not as noise to be smoothed out, but as a set of possibilities to be explored. If Andromeda's sideways drift is at the low end of what current data allow, the collision happens. If it is at the high end, the two galaxies swing past each other and never really meet. If the large Magellanic Cloud's mass is a bit larger than we currently estimate, the whole trajectory shifts. If Andromeda is a bit less massive than we currently believe, gravity has less to work with, and the merger is delayed or avoided. 22 variables, each with its own range of plausible values. And when you sample all of that space, honestly and without preconception, what you find is that the future of the two largest galaxies in our local group is not one story. It is a whole ensemble of stories. Some end in a spectacular head-on merger. Some end in a graceful near miss. Some end in a slow inward spiral that takes 15 or 20 billion years. And a large fraction of them end with the two galaxies still separate, still drifting, still not quite touching at any point in the next 10 billion years at all. This is not a small revision. This is a fundamental change in how we think about the fate of our galaxy. For over a century, we have been telling ourselves a story of certainty. And what the new science is quietly saying is that we do not, in fact, know. Not with confidence. Not yet. What we know is that the two galaxies are close, that they are massive, that they are moving, and that within the current uncertainties, the outcomes are wide open. Till Sawala, describing the result to the press, put it in almost gentle terms. He said that until now we had thought this was the fate awaiting our Milky Way, and now we know that there is a very good chance we may avoid it. His colleague, Carlos Frank at Durham, said something even more careful. He said that we do not yet know if the collision is definitely off in the future, but that the confident story of an inevitable collision that will destroy both galaxies is not as certain as people have been told. Now, I want to be very honest with you here, because it would be easy to overshoot in the other direction and tell you the collision has been canceled. That is not what the science says. What the science says is subtler. It says that the collision, in the classic 4.5 billion year window, is now much less likely than we thought, and that over the longer horizon of 10 billion years, it becomes something like a coin flip. That is a very long window in which many things can happen. Even if the two galaxies do not merge in that window, they may still make close passes, close enough to distort each other, close enough to trigger starbursts, close enough to redraw the night sky. Even a near miss between two galaxies of this size is one of the more dramatic events in cosmic history. The complete cancellation of any interaction whatsoever is not on the table. What is on the table is the specific, tidy, cinematic ending we had grown attached to. That ending has become one possibility among many. And here is another quiet subtlety I want to name, because it matters. The new numbers are based on the very best current data, but that data itself is going to get better. In the summer of 2026, the European Space Agency's Gaia mission is expected to release a new set of measurements, a great catalog of stellar positions and motions across our galaxy and beyond, which will sharpen the estimates of Andromeda's sideways drift. And within a few more years, ongoing analysis from Hubble and from the newer James Webb Space Telescope will refine the mass estimates further. Every one of these improvements will narrow the range of the 22 knobs, and every narrowing will change the odds. It is entirely possible that within the next decade, the same team, running the same simulations with newer data, will come back and say either that the odds have swung back toward collision or that they have swung further away. This is the honest condition of the science right now. We are inside a moment of live revision. The number, as of tonight, is roughly a 50-50 coin over the next 10 billion years, and less than 2% inside the old confident window. But that number is going to keep moving. What matters is not the exact digits. What matters is the shape of the change. And the shape is this. The old certainty is gone. The story has become a probability distribution. The picture in the textbook has become a cloud of possibilities. There is something quietly beautiful in that when you sit with it. Because for a long time, our own galaxy's fate has felt written, fixed, determined, something we could point at and describe with confidence. And what these new simulations are really telling us is that even at the largest scales in nature, the future is not a fixed line. It is a fan of possibilities whose edges depend on tiny details we cannot yet measure, on the exact sideways drift of a galaxy 2.5 million light-years away, on the exact mass of a small satellite galaxy hanging off the edge of our own, on the way gravity, that oldest and simplest of forces, adds up its consequences across time so long that no human intuition can quite hold it. The future of the Milky Way, in a very real sense, has just become less knowable. And less knowable, it turns out, does not mean less interesting. It means more interesting, more alive. And so let us hold both stories in our minds at the same time. The old story, the tidy one, in which Andromeda comes toward us, and the two galaxies merge into Milkomeda in a great cinematic embrace 5 billion years from now. And the new story, the truer one, in which the coming together is only one of many possible endings, and in most of them on the timescales we can currently trace, the merger happens later, or partially, or not at all. Both stories are, in their own ways, real. Both stories describe something the universe is really doing, and both stories, in the end, will be replaced by better ones as we learn more. That is what science does. It replaces confident pictures with more honest ones. And the more honest picture in this case is a much stranger, much more open-ended picture than the one in the textbook. Before we take our next step, I want to ask you something. Because this, I think, is one of the most personal questions in the whole video. When you first heard tonight that the collision might not actually happen, that the tidy story of Milkomeda might be less certain than you had been told, how did it feel? Was there a small, quiet relief in it? The way there is sometimes a relief in learning that a hard thing you had been told to expect might not come? Or was there, strangely, a small disappointment, the way you might feel when a movie you had been waiting to see turns out to be canceled? There is no right way to feel this, but I am genuinely curious. Because the answer says something about how each of us privately relates to the future of the sky. Tell me in the comments. I would love to know. Because in a moment, we are going to take one last step, and it is the biggest one of all. Because so far, we have been treating this whole story as if the question at the center of it were a good question. Will the two galaxies collide? Will they merge into Milkomeda? Will there be a Milkomeda at all? We have taken the question seriously, and we have followed it through several layers of revelation. But in the last part of this video, we are going to step back one more time, and we are going to ask something quieter and stranger and much larger. We are going to ask whether the question itself was really the right one. Because when you widen your gaze enough, when you take in enough of the surrounding universe, and enough of deep time, the question of whether two particular galaxies collide begins to dissolve. And what appears in its place is something much harder to hold and much more beautiful. So let us step back. Not one step, not two. Let us take the biggest step back we have taken in the entire video, and let us do it slowly. Because everything we have been discussing so far, the collision, the timeline, the ghost dance of trillions of stars, the birth of Milkomeda, the new probabilities that make her uncertain, all of it has been framed around a single question. Will our galaxy collide with Andromeda? It is a good question. It is a question that has driven a century of astronomy. It is the question that got you to click on this video tonight, and it is the question that has carried us through 6 long acts of storytelling. But I want you to sit with something quietly before we go any further, because I have been carrying this thought since the beginning of the video, and I have not yet been able to shake it. And it is this. The question, when you step back far enough, begins to dissolve, not because it is a bad question, but because the words inside it, all of them, will they, we, collide us, our galaxy, begin to lose their footing. And what is left behind when the question falls apart is something much stranger and much quieter and, I think, much more beautiful than any answer we could have arrived at. Let us start with the smallest of those words, the word we. When we ask, will we collide with Andromeda, what does that we refer to? It cannot mean you and me sitting here tonight on a small, warm planet in the year 2026, because you and I will not be here, not in 5 billion years, not in 1 billion, not in 100 million. The oldest human civilizations we can point to are only a few thousand years old. Our entire species in its current form is somewhere between 200,000 and 300,000 years old. The very earliest members of the genus Homo, our distant ancestors, appear in the fossil record only a few million years ago. And even if you are extremely generous, even if you count every one of them, every hominid, every ancestor, every branch of the family tree, we as a lineage still occupy a sliver of time that is, on the scale of the merger, essentially invisible. The whole of human history, from the first stone tool to the last email you sent today, would fit inside the merger timeline the way a single blink fits inside a lifetime. Perhaps not even that. So the we in the question is not us. It cannot be. Whatever will be here to witness the coming of Andromeda, if anything is here at all, will be so distant from us in time and biology and mind that we cannot really call them us in any meaningful sense. They may be descendants. They may be strangers. They may be nothing, silence, an empty planet under a slowly warming sun, but they are not us. Now let us pull the next word out of the question and hold it up to the light. The word our galaxy. This word rests quietly on an assumption of ownership, or at least of belonging, as if the Milky Way were something we possessed, as if we had some special relationship to it. And yet at the scale of the galaxy, the Sun and its little family of planets are one out of somewhere between 200 billion and 400 billion star systems, tucked along the inner edge of an unremarkable spiral arm called the Orion Spur, in an outer suburb of the disk. More than 25,000 light-years from the galactic center, there is nothing about our position that is central. There is nothing about it that is chosen. We are one small pinprick among hundreds of billions. And even our tenancy, our permission to sit in this particular seat of the galaxy, is temporary. The Sun is a middle-aged star with about 5 billion good years left in it. After that, it will die. And whatever descendants of ours, if any, still exist, will either have left this solar system or perished with it. In neither case will they still be around when the merger reaches its final act. So the word our, applied to the galaxy at cosmic timescales, is a little like a mayfly claiming ownership of a river. Now let us pull the next word, the word collide. We have already seen in a previous section of this video that this word does not really describe what happens when two galaxies meet. Nothing collides in the ordinary sense. Not the stars, not the planets, almost nothing that we can point to and touch. What actually happens is a slow, gravitational entanglement, an inward spiral, a gentle merging of two nearly transparent structures that pass through each other more like clouds than like solid objects. The word collide, borrowed from our human world of cars and billiard balls and colliding waves at a beach, is deeply misleading. It suggests an impact. It suggests a moment. And there is no impact and there is no single moment. There is only a long, slow, silent embrace unfolding across billions of years. And now let us pull the last and most surprising word out of the question, the word Andromeda, because even Andromeda is not really a thing. Or rather, she is a thing in the same way that a river is a thing. She is a coherent pattern that we have chosen to give a name to. But the stars that make her up are individually just stars. They orbit their center. They live and die and are replaced. The Andromeda you see in the sky tonight is not the Andromeda that existed 100 million years ago. Many of the stars have moved. Many have died. Others have been born. The pattern has drifted subtly into a new configuration. And in another 100 million years, the pattern will have drifted again. The idea of Andromeda, the galaxy, as a single object with a fixed identity is our idea. It is not really her idea. If she has an idea, and of course she does not, it is not this one. She is a river of light, and rivers do not know that we have given them names. So when we ask the question, will we collide with Andromeda, and we widen our gaze enough to see it properly, the question gently begins to lose its footing. There is no we. There is no our galaxy in the possessive sense. There is no collide in the sense we usually mean it. And there is no Andromeda in the sense of a fixed and enduring object. There are only patterns. There are only rivers. There are only rearrangements of light and mass, spread across a stretch of time so long that nothing we call a person could ever span it. And here is the part that I find, the more I think about it, the most humbling of all. Because we have not yet reached the largest scale in this story, we have not yet zoomed out to the widest picture, there is one more layer. And this is the layer that, when I first understood it, quietly rearranged the way I think about our galaxy and Andromeda and Milkomeda and everything. Because the universe, as we discovered 100 years ago and have been confirming ever since, is not standing still. It is expanding. And it is not just expanding. It is expanding faster. The rate of expansion, driven by whatever it is we clumsily call dark energy, is accelerating. Every year, every second, the space between distant galaxies grows faster than it did the year or the second before. And this has consequences that are almost too large to hold in one thought. Inside our local group, gravity has already won. We have said this. The 100 or so galaxies bound together with us, including Andromeda and the large Magellanic Cloud and Triangulum and dozens of small dwarfs, are bound by their mutual gravity, and they will stay bound. The expansion of the universe cannot tear them apart. They are stitched to each other. They are a family. But beyond the local group, every other galaxy is drifting away and accelerating away, and the ones that are farthest away are receding fastest of all. In tens of billions of years, the acceleration will be so severe that essentially every galaxy outside our local group will have drifted beyond what cosmologists call the cosmic event horizon. Their light, sent out from where they now are, will never reach us. Not because our telescopes are not big enough, but because the space between us and them is expanding faster than light can cross it. They will slip out of our sky forever. And the sky above Milkomeda, if she forms, will not be the sky of a rich, populated universe filled with countless other galaxies. It will be the sky of a lonely island. A single glowing elliptical galaxy, drifting in a void so complete that no other galaxy is visible in any direction. Not with the naked eye, not with the largest telescope any future civilization could ever build. Just Milkomeda and the dark. Take that in for a moment. Because if you were a citizen of a civilization living inside Milkomeda 100 billion years from now, and you had the equivalent of our telescopes, and you turned them on the sky and asked what is out there, the honest answer would be, only us, only this one galaxy, only this quiet elliptical drifting alone through an infinite black. You would not know from anything you could see that there had ever been other galaxies. You would not know about the local group. You would not know about the merger. You would not know about the Milky Way or Andromeda, because those names would refer to things so long ago dissolved into your own galaxy that no trace of them, as separate objects, would remain. You would look up into an empty sky, and you would assume, quite naturally, that you were alone, that the universe had always been this way, that your one galaxy was, in some sense, all there was. The last galactic collision, the one we have been talking about all night, is not just the last chapter in our galaxy's story. It is very close to the last dramatic event, on the largest scale, in the entire cosmic story of our neighborhood. After Milkomeda forms, whether that happens in 5 billion years or 10 or 15, nothing much more will happen. The stars inside will burn down. New stars will be born less and less often as the gas is used up. The whole galaxy will slowly grow redder and dimmer and quieter. The other galaxies of the observable universe will drift out of view, and Milkomeda alone in the dark will simply sit there glowing softly for tens of billions of years, and then hundreds and then trillions, until at last her last star flickers out and the sky and the universe and any question we could ever have asked about them all fall into silence together. That is the true scale of the story we are inside. That is the answer, if we are honest, to the question that started this video. Will we collide with Andromeda? There is no we. There is no permanent us to whom the collision could happen. But there is a slow, breathtaking transformation coming. It is coming whether we like it or not. It will happen after we are gone. It will happen in silence. It will not be witnessed by any human eye. And it will be, at least in one possible ending, the last great cosmic event before the long, dark, cooling silence of the deep future begins. And yet, I do not want to leave you in that silence just yet. Because there is one more small thing I want to say, and it is the most important thing in the entire video, and it is the reason, I think, that we tell each other stories like this in the first place. Because even though we will not be here to see it, we are here now. Right now, tonight, wherever you are, in a warm room or a quiet car or a bed lit by the pale glow of a screen, you are alive. You are made of atoms that were forged inside stars that died before our sun was born. You are looking up at a sky that contains a bright, soft smudge 2.5 million light years away, and you know what it is. You know its name. You know what it is doing. You know tonight, more than any human being who has ever lived before this century, what your galaxy is, and where it is going, and what may happen when it meets its neighbor in the dark. That knowing is a small, brief, warm little flame inside a very long, very cold, very old universe. And I do not think it is nothing. I think, when you sit with it long enough, it may be the most surprising thing about the whole story. that the universe, in some inexplicable way, has arranged itself so that a small conscious creature on a small blue planet can, for a brief window of cosmic time, hold this entire picture inside a single mind. Let me ask you one last thing before we begin to bring this to a close, because this one, I think, is the most personal question in the whole video, and I really do want to know how you answer it. Sitting where you are right now, having walked through all of this with me, do you find it lonely that no descendant of ours will see Milkomeda in the sky? Or do you find it strangely comforting that you are here, right now, in the very small window when knowing about it is even possible? Is it a loss that we will not be there? Or is it a gift that we get to think about it here? I have my own answer, but I would love to hear yours. Tell me in the comments. I will read every one, because in a moment we are going to bring this whole long night to its close. We are going to retrace the journey we took together, gently, in the way you might turn a stone over in your hand one last time before setting it down. We are going to sit for a while with the softness of everything we have learned. And then at the very end, I will ask you one small favor, and I will say good night. And so we have arrived, you and I, at the quiet end of a very long walk. Let us take a moment before we say good night to look back over the ground we have covered, not in the way you might summarize a lecture, but in the way you might, at the end of a long day of traveling, sit on the porch of a small house and let the day settle in your mind, piece by piece, softly, without hurrying. We started with an image, a picture in a textbook. Two spiral galaxies tilted toward each other with a confident arrow drawn between them and a confident number underneath. 4.5 billion years, a collision, a merger, a tidy sentence at the end of a chapter. And we agreed together at the very beginning of this video that we would take that tidy sentence apart, not to spoil it, not to destroy it, but to see what it was hiding. And what it was hiding, it turned out, was almost everything. It was hiding a small, patient man in a cold observatory in Arizona in the year 1912, who bent his eye to a spectrograph and became the first human being ever to measure the motion of a galaxy. It was hiding the fact that the very first galaxy he ever measured, out of every possible galaxy in the sky, happened to be the one that was falling toward us. It was hiding 100 years of quiet argument about what Andromeda even was. And the moment in the 1920s when Edwin Hubble finally proved that the small cloud Al-Sufi had written about 1,000 years ago was not a cloud at all, but another galaxy, another city of stars, another island universe drifting in a sea of darkness. It was hiding the strange fact that almost every galaxy in the observable universe is running away from us. And this one, this particular bright neighbor, is one of the very few coming home. The picture was hiding, also, the emptiness inside a galaxy, the staggering emptiness. The way that a galaxy up close is not the thick river of light we see from a distance, but a vast, quiet, almost transparent structure in which the average star is separated from its neighbors by trillions of miles of nothing. It was hiding the ghost dance. The realization that when two galaxies meet, almost nothing collides at all. that trillions of stars pass silently through each other in the dark, missing each other by unfathomable margins, and the whole event at the scale of individual worlds is a slow, silent, near-miss unfolding over billions of years. It was hiding the true actors of the drama, the invisible dark matter halos that surround each galaxy like a second, larger body, the ones that are already, quietly, beginning to overlap out in the deep dark between us and Andromeda tonight. It was hiding the tidal streamers, and the starbursts, and the exiled stars flung out into intergalactic space to drift, alone for the rest of eternity. It was hiding the two supermassive black holes, ours and hers, who will one day find each other at the center of a new galaxy and ring the fabric of space-time like a struck bell. And it was hiding a future sky. We walked out into that future sky together. We stood in our minds on the surface of a warming Earth, 500 million years from now, and watched Andromeda begin to grow. We stood there again 2 billion years from now and watched her fill the horizon. We stood there 3.5 billion years from now and watched the two galaxies pass through each other in a great silent embrace. And we watched the constellations of 100,000 years of human sky-watching dissolve into an entirely new arrangement of stars. And then we stood at the end, 5 to 6 billion years from now, watching the birth of Milkomeda and the death of the sun happening in the same quiet window, a cosmic coincidence of endings and beginnings, all in the same breath. And then the picture cracked one more time, because just last year in the summer of 2025, a small team of astronomers in Finland and England and France ran 100,000 simulations of the future of the local group and quietly, politely showed us that the collision we had been telling ourselves was inevitable had become, in the light of the newest data, a coin flip at best. Not cancelled, but no longer certain. The old confident story had become a cloud of possibilities. The tidy arrow had softened into a probability distribution. The future of our galaxy, which had seemed so decided, turned out to be far more open than any of us had thought. And then, in the last section, we did something quieter still. We stepped back one final time, and we noticed that the question itself, the question we had built the whole night around, will we collide with Andromeda, was not really a question we could ask cleanly, because there is no we who will be there. There is no our galaxy in any permanent sense. There is no collide in the way we usually mean the word. And there is no Andromeda in the sense of a fixed object with a single identity. There are only patterns, only rivers of light, only slow, immense rearrangements of mass and time, drifting toward each other in the dark, quite indifferent to whether or not we watch. And that, if we let ourselves feel it, is a strange and humbling thing. Because the sky we grew up under, the sky we take for granted, is a temporary sky. It is a sky in a particular configuration, at a particular moment in cosmic history, that will never look quite this way again. Every constellation you learned as a child, every star you have ever wished on, every pattern that has ever meant anything to any human being ever, is a temporary arrangement in a slowly rearranging universe. In a few million years, they will look slightly different. In a few 100 million, they will be unrecognizable. In a few billion, the whole framework of the sky will have dissolved into something else. And past the birth of Milkomeda, past the last galactic event of our neighborhood, the sky will begin its long, slow slide into the dark. As the rest of the universe drifts beyond the horizon and Milkomeda alone glows softly against nothing for tens of billions of years, until even her stars burn out one by one into silence. That is the honest picture. It is not the picture in the textbook. It is bigger and stranger and softer and lonelier and, I think, more beautiful. And here is what I want to leave you with before we say good night. Because it is easy at the end of a video like this to feel small, to feel like a speck, to feel like a brief flicker of consciousness in a universe that will barely notice you were here. And on one level, that is exactly what you are. On one level, it is exactly what I am. But there is another level, one that I do not think we take seriously enough, and I want to name it before we go. You are, right now, a piece of the universe that has arranged itself into the ability to know about all of this. Think about that for a moment. Somewhere between 14 billion years ago and now, in a great slow chain of hydrogen becoming helium and helium becoming carbon and carbon becoming everything out of the dust of dead stars, and the slow chemistry of a small blue planet matter has, against every ordinary expectation, sat up and started to wonder about itself. It is doing that right now in your body. It is doing that right now through your eyes and ears and mind. The atoms in you were once inside stars. The stars they were inside once shone in a sky far more crowded than this one. And now, tonight, those same atoms are listening to a story about the sky, about a galaxy that lives 2.5 million light years away, about a collision that may or may not happen billions of years after you are gone, about the deep, dark, quiet fate of the entire local universe. And they are following it. They are understanding it. They are, in some small way, holding the whole thing inside a single mind. I do not know what to call that other than a small miracle. Not a supernatural miracle, not a magical one, just a quiet, physical, once-in-a-cosmic-age miracle. A brief window on a small planet when the universe grew a piece of itself that could look back at it and say, oh, so this is what has been happening. So this is what we are inside of. So this is the story. And that is what I want you to take with you tonight from all of this. Not fear, not smallness, not despair at how brief we are, or how far away Milkomeda is, or how impossible it will be for any child of ours to ever see the sky we have painted together tonight. But the quiet strangeness of the fact that right now you knew. That right now you got to hold it. That the atoms of Andromeda's ancient light, traveling for 2.5 million years across the dark, arrived briefly in the mind of a small conscious creature on a small blue planet and were understood. That happened tonight. It is happening right now. It is one of the loveliest facts in the universe, and it is entirely, quietly yours. If you have made it this far with me, all the way to the end of this long night, thank you. Genuinely, thank you. It means more than I can easily say. If this kind of slow, deep exploration of the cosmos is something you would like more of, a small like, or a quiet subscribe, or leaving a comment sharing which part of this video stayed with you the most, would help this channel enormously. It is a small thing for you and it is a large thing for me. That is the last time I will ask. Thank you sincerely for listening. And now, wherever you are, I want you to do one small thing before you sleep. You do not have to move. You do not have to open your eyes. You do not have to do anything but breathe. Just in the quiet of your own mind, hold, for a moment, the picture of a soft, bright smudge hanging in the sky above the constellation Andromeda, 2.5 million light-years away, drifting toward us for the entire history of everything you have ever loved. Hold that picture gently. Let it sit inside you for a breath or 2 or 3. And then when you are ready, let it go. The sky will keep changing without us. That is all right. That was always going to be the case. The 2 galaxies will do whatever they are going to do over timescales that no human heart can hold, and it will be beautiful whether we are there to see it or not. But tonight, you were here. Tonight, you got to know about it. Tonight, you got to walk out to the edge of the deep future with me and stand there for a while, under a sky that will never quite come. And that is, I think, more than enough. Rest well, small conscious creature in your small warm room on your small blue planet, inside your one particular quiet galaxy drifting through the dark. Sleep well under the stars. Good night.